In this video, we evaluate the integral of e to the power minus x square cos x dx as x changes from 0 to infinity. We'll do it by Feynman's technique of integration, whereby we'll simply be differentiating under the sign of integral. Let's do it. Observe that you may speculate that we will simply do it by integration by parts. Integration by parts says if we got product of two functions and if we want to integrate those, let u be the first function and v be the second function, then integral of product of two functions is given by first function times integral of second minus integral of derivative of first times integral of second, and this product has to be integrated once again. So let's try to do it. First function is e to the power minus x square. Integral of cos x is sin x minus integral of derivative of first function. If you differentiate e to the power minus x square, you get e to the power minus x square, and then you need to differentiate minus x square, that is minus twice x, and then integral of cos x, integral of second function is sin x. As you can see that we get much complicated expression than we have started with. In fact, we won't be able to do it by integration by parts. However, we'll be able to do it by using Feynman's technique. Let us do it. Let us assume this integral to be equal to IB. This is a reasonable assumption because if we change the value of b, then we will get different value of the integral. So this integral is a function of b. So what we are doing is, instead of evaluating e to the power minus x square cos x dx, we will just take b equal to 1 and then find the value. So as we said, we want to do it by differentiating under the sign of integral. Let's differentiate both sides with respect to b. ddb of ib equal to ddb of this integral. Now we see that integral is nothing but a long sum. You see this symbol s. If I write it simply long, then I'll get integral. And we know that derivative of sum equal to sum of derivative. So what we can do is that we can write this derivative inside the integral. That's the technique all about. But you see that inside the integral we have two variables x and b. So what we'll do it, we'll partially differentiate with respect to b. Can we partially differentiate? Of course. When we say partial differentiation with respect to b, then we regard x to be a constant. So derivative of e to the power minus x square we don't have to worry about. Derivative of cos is sine. So sine of b of x and then we need to differentiate bx with respect to b. You see that derivative of b with respect to b is just 1 and derivative x is just a constant, so we get this expression. Now let's rewrite this expression as integral 0 to infinity sin bx times e to the power minus x square times x dx. Now you see that I can regard this as second part and this one is a first part, and we can evaluate by integration by parts. So this is, we can regard it as a product of two functions. Can we evaluate the integral of e to the power minus x square times x dx? Of course, yes. However, integral of e to the power minus x square times x dx, we simply write x dx is half of d of x square and e to the power minus x square as it is. Now it is something like e to the power minus u du, and integral of e to the power minus u du is e to the power minus u by minus 1 plus some constant of integration. Oh, I happen to make a slight mistake. You see, if we differentiate cos, I get minus sine. So let's write minus sine and then minus sine. And so di db equal to minus sine bx and then product of e to the power minus x square x dx. Now we apply integration by part to the integral of sine bx times e to the power minus x square times x dx. That's equal to first function is simply sine bx, and then integral of e to the power minus x square times x is e to the power minus x square by minus 2, first time integral of second, minus integral of derivative of sine bx. Derivative of sine bx is minus of derivative sine bx is simply cos bx, but we are differentiating with respect to x, so times b. And then integral of e to the power minus x square times x is e to the power minus x square by minus 2 dx. So we can write di db equal to minus, we can write outside of the integral, and then we apply the limit 0 to infinity sine bx e to the power minus x square by minus 2, once again 0 to infinity, negative of negative is positive, so plus integral of negative positive, but we got one more minus there, so minus b by 2, that's just a constant, cos bx times e to the power minus x square dx. Now as x approaches infinity, e to the power minus x square approaches 0. As x approaches 0, or rather if we choose x equal to 0, sine 0 is 0. So we get 0 minus b by 2. You see that we get something similar to what we have started with. You see that ib is simply equal to integral 0 to infinity e to the power minus x square cos of bx dx. Let's write it ib. ib, or simply write I. Okay, so we get a cute expression. Let's say di db equal to minus b by 2i. Can we integrate it? Of course. We simply write it as 1 by I di equal to minus b by 2 db. Now in integrated both sides, integral of 1 by I di is log of I, of course with base e, equal to minus half of integral of b with respect to b is b square by 2. So it turns out that, of course, with plus some constant of integration, I equal to e to the power minus b square by 4 times e to the power constant, that's another constant. So ib turns out to be constant time e to the power minus b square by 4. Can we evaluate this constant? Of course, yes. Let's look at the expression ib equal to integral 0 to infinity e to the power minus x square cos of bx dx. When I choose b equal to 0, it's simply e to the power x square dx. Sorry. If I choose b equal to 0, it is simply e to the power minus x square dx. So I0 equal to integral 0 to infinity e to the power minus x square dx, and that is exactly equal to root pi by 2. So if I write b equal to 0, then I0 is root pi by 2, turns out to be c1 times e to the power 0, which is just 1. So it turns out that c1 equal to root pi by 2. If we substitute the value of c1, then we get ib equal to root pi by 2 e to the power minus b square by 4. Okay, what is ib? ib is this integral. So we just write it and we are done. And so integral of e to the power minus x square cos of bx dx is x change from 0 to infinity turns out to be root pi by 2 e to the power minus b square by 4. But we want the value corresponding to b equal to 1. So we choose b equal to 1 to show that integral 0 to infinity e to the power minus x square cos x dx equal to root pi by 2 e to the power minus 1 by 4, and we are done.